Let's explain Kirchhoff rules for electric circuits. These are essentially two rules of utmost importance for analyzing electric circuits. One is about the currents approaching towards a junction, and the other one is about the potential drops when you go around a loop. So let's start with the junction rule. This says that this is one form, that the sum of all currents flowing towards a junction is zero. This is actually quite easy to understand. We have actually discussed the situation about the current on a single wire. We have asked the question whether the current is the same everywhere on the wire. There's a similar kind of a situation in here. If you just think about this junction in here as a physical system, the total charge at that junction, or the rate of change of that the charge at that junction, is given by the sum of all of these currents. So this expression is actually the rate of change of the charge right at the junction. Okay, and in the electric circuits, we said that in most of the steady state situations, in any case, that there is no charge pileup. So as a result, the charge around this junction does not change with time. So as a result, this rate of change should be equal to zero. This tells us that the sum of the currents are equal to zero. So that's basically this physical constraint that tells us that the currents on branches that are connected by a junction are related to each other. So in reality, of course, we just express one of the currents in terms of the three others. Okay, so there are other alternative expressions. Instead of saying the currents flowing towards a junction, you can also talk about the currents flowing away. It's just a change of sign, actually. So a current which is flowing away from the junction is the negative of the current which is flowing into. And so as a result, it's going to be the same statement. So in that case too, we can say that the sum of the currents that are flowing away from the junction is equal to zero. So that's the statement in that case. So that's an equivalent statement. But of course, in reality, most of the time when we draw the arrows on the branches, we cannot choose them in such a way that they are in the same direction around the junction. So they are going to be in various different directions. So in that case, this last expression is perhaps a little bit more useful. So the sum of the currents flowing towards a junction is equal to the sum of the currents which are flowing away. So in this diagram in here, we have two currents. Basically this I1 and I3, which are flowing towards the junction. And the three currents, I2, I4, and I5, these are flowing away from the junction. And so therefore the sum of these I1 and I3 should be equal to the sum of the other three currents. In none of these examples, we are claiming that any of these currents are positive. Okay, so when I say arrow is towards that junction, I'm not claiming that I1 is positive. I1 can as well be negative. Usually, when we are solving circuit problems, before the solution, we don't know what the direction of the current is. So as a result, we have no idea of what the direction of the current at. Before assigning this arrow direction. So we first assign the arrows, write down the equations, and then solve the circuit problem. And at the end, it might appear that this I1 is negative. But of course, we won't stop and resolve the same problem again, because we know that this is also physically meaningful, and all of these equations are satisfied in the same way. So as a result, we have no insistence of making sure that the currents are always positive. Okay, let's pass to the loop rule. The loop rule says that the sum of the potential changes around a loop is zero. So that's also very simple. Let's say that you start from this point in here, from point A. You just then go around. So this arrow shows the direction where we go around the loop. So if we first pass to B and then to C and then whatever, at the end we just come back to the original location that we have started with. So as a result, when we are traveling around the loop, if I just compute the changes in the potential and then sum them up, I'm going to find the total change in the potential. So that means it's going to be VA minus VA. So it's final minus the initial, but they are the same. So therefore, the total change in the potential should be equal to 0. Again, this is a physical constraint. It's a constraint that basically electric field is conservative. Potential is a well-defined function of position. And so therefore, the sum of the potential differences should be 0 when you go around the loop. Okay. In this case too, I don't have to talk about potential differences. I can also express the same expression in terms of the potential drops. That's also an alternative. It's a nice alternative, especially if there are resistors. This might be a better way of thinking about it. And of course, this is not it. That's not the final bird. There's yet another alternative expression. Basically, you may want to treat the EMF devices differently from the resistors. And so as a result, you may want to compute the potential changes when you go across an EMF device and potential drops on the resistors. In that case, the rule basically says that, you can move one of them to the other side of the equation. So instead of writing the potential drops for EMFs on the right-hand side, I can move them to the other side. In that case, that's going to be the changes of the potentials when we are crossing the EMF devices. And so as a result, I can write down the expression for the loop rule like this, in this form. Okay. So a few examples would be very useful. Let's start with this one. Okay. So by this, I'm actually implying that this is part of a bigger loop, bigger circuit. So there are parts of that circuit in here, which might be very complicated. I don't care. I'm just considering this loop in here, that particular loop. Let me draw the loop like that. Right? Let me go over the loop with a highlighter. So this is the loop that I'm talking about. So we start somewhere and go around the loop. But when we are going around the loop, of course, I need to choose some direction. Without a direction, I cannot be consistent. So let's say that I'm going in this direction, in the clockwise direction. So when I'm going around the loop, I just count the EMF devices. So first I see, for example, the EMF device E3 in here. If I start from that particular point, I see E3 and then I see E1. So therefore E3 plus E1, of course the order is not important, is equal to, now I write down the potential drops on the resistors. So potential drop on the resistor R1 is, this is always the case that when I'm going along the direction of the arrow where this current is measured, the potential drop is counted as a positive quantity. So as a result, this is I1 times R1. So for this resistor, it is I2 times R2. And then finally, for the third resistor, it's going to be I3 times R3. Right? So as a result, the loop rule written down, that particular loop of that circuit would be like that. Okay, there are some sign conventions, of course. When you choose the direction on the loop, that direction may not coincide with the direction where the currents are expressed. So there are these kind of situations. And also you may go over an EMF in the opposite direction of its given polarity. Let's see how we can handle these kind of situations. So let's just look at this simple case. So this is the direction that I'm going to follow the loop. When I go around this loop, in this direction, I see only an EMF. So therefore, the sum of the EMFs is equal to E. Right? When I'm going around this loop, when I go over this resistor, I am going parallel to the direction where the current I1 is measured. So that's the direction. So therefore, for this one, I'm going to write down the potential drop as I1 R1. And then when I'm going over R2, I'm moving in that direction, but the current is measured in the opposite direction. So therefore, in the direction that I'm moving, the current is minus I2. And so therefore, I have to write this thing down with a negative sign. All right, so therefore, for that loop, therefore, the loop rule reads as I1 R1 minus I2 R2 is equal to the EMF. Okay, I can also explain it like that. All right, let me draw that part of the circuit again. Okay, so the current on R1 towards right is equal to I1. That's, of course, the original direction that it is measured. And the current on R2 in the downward direction is minus I2. So that's the current in here. And that's the EMF. So when I go around that loop, I see an EMF that's equal to I1 R1 plus minus I2 R2. All right, it's the same thing. The reason why we are writing minus 1 in here is because if I express the current in the with an arrow in the opposite direction, then it would appear with a negative sign. This is the last example. In that case, there are EMF devices which are opposite in polarity. Let's again consider this loop in here. This is the loop direction, right? We are going around like that. So in that case, let me first write this thing down like that. This is sum of the EMFs is equal to sum of the potential drops on the resistors. So sum of the EMFs, when I am going along this direction, let me also show the direction with a highlighter. E1 is positive. I'm passing opposite to E2. And then I'm passing parallel to E3 away. So therefore, the sum of the EMFs would be E1 minus E2 plus E3. Right? And for the sum of the current times the resistances, the first, for R1, the sign is positive, so that's I1 R1. For R2, the sign is negative, so it's minus I2 R2, and there's nothing else, right? That's the rule. All right. I can also express the loop rule by choosing the loop in the opposite direction. So I could have chosen the direction of the loop like that. I could go around the loop like this. In this case, I'm going to write down the equation like that. Let me also use a highlighter and express what I see. Let's say that I start from this point. I move along that direction. So first I see E2. This is positive. Then I see E1 in the opposite direction. So that's minus E1. And then I see E3. That's also in the opposite direction. So therefore, this is minus E3. And then come back. All right. So as a result, let me use a yellow color for this. In this case, I'm going to write E2 minus E1 minus E3. And on the other side, I have, let me use the highlighter again. Again, I started from here. And then when I'm passing over R1, I'm passing opposite to I1, the current. So therefore, this is minus I1 R1. And I'm moving in the same direction over R2 with the current. So therefore, this is plus I2 R2. So let's also write this thing down with yellow. Minus I1 R1 plus I2 R2. Right? As you can see, I have obtained the same equation except that I multiplied both sides with minus 1. So that means that if I choose the direction of the loop in the opposite way, I essentially multiply both sides of my equation with minus 1.